So this video we have a RLC circuit. So we have RLC, right? Resistor, inductor, capacitive circuit. So we have the resistor, which has 600 ohms of impedance. We have the inductor, which has 5,000 ohms of impedance. And so being an inductor, of course, there's a J term here where there's a 90-degree phase shift, right? And we have a capacitor with 1,000 ohms of impedance, okay? Technically, remember the capacitor is inductive, capacitive reactance. The inductor is inductive reactance, but that is what is impeding the flow of current. So the capacitor is going to have a minus J or a minus 90-degree phase shift. So this is a simple series circuit. So we have that the total impedance Z, so the total impedance Z is the resistances added up, in this case we just have one resistor, plus all the inductive reactances added up, plus all the minus, actually, because it's a negative, right? So minus all the capacitive reactances added up. And so when we look at this, then we're going to see that our total impedance, I've actually got it written down here, is 6 kiloohms plus J 5 kiloohms minus 1 kiloohm. And so, you know, we can simplify that by just saying 6 kiloohm plus J 4 kiloohms. And of course we can see that the voltage is 100 volts at an angle of 0. So it's our reference voltage, so we have the voltage set at 0. So we can calculate then, using Ohm's law, we can calculate the current as being the voltage divided by the impedance. And so that would be 100 at an angle of 0 divided by 6K plus J4K ohms. And if we punch that then into our calculator, so I'm going to use the Octave software here. Clear my screen. And so we have 100, since it's angle 0, we don't have to worry about the angle, divided by parentheses 6. Now I'm not going to put in 6,000 or 6e to the 3 because I'm just going to remember that they're both kiloohms, and so when I'm done I'm going to end up with the milliamperes. And so 6 plus J times 4, and this is going to give me the current, so I'm actually going to stick that in a variable called I, so that'll be my current. Now again, this is the rectangular form of the current, which really is, it's a valid value, but a little harder for us to see what the magnitude is. So what I like to do is convert it to polar. So I'll just create a second variable called polar. I'll take the absolute value of the current, and then I'll take the angle of the current. And the angle of the current using this function gives you radians. So I'm going to multiply it times 180 degrees and divide by pi radians to get it into angles. And so I get the current actually turns out to be 1 milliampere, because remember there was a K in there, so it's going to be 1 milliampere with an angle of minus 33 0.7 degrees to the third significant digit. Alright, so let me just kind of write that down here. And so we have an angle, so the current I then is going to be 1.00 milliamperes at an angle of minus 33.7 degrees. Now, we know, remember Eli the Iceman. Alright, so I've got I've got an inductor and I have a capacitor, but these two are opposing each other. So the largest one is basically going to win. These guys basically play tug of war, and the largest one's going to win. So we obviously can see that the reactance, the inductive reactance is 5,000, where the capacitive reactance is only 1,000. So in this particular case, the inductive reactance is obviously going to win, and so that's why we have the voltage, which has an angle of 0, and the current has a negative angle because it is behind the voltage. Right? Eli the Iceman. So in an inductor, the voltage is ahead of the current, or the current is behind the voltage. Right? So voltage is our reference point. It has an angle of 0. So I'm expecting a negative angle for my current. So now we can just apply Kirchhoff's voltage law, KVL. So we can do KVL and find the voltage of each of these elements. So the voltage drop across the resistor, VR, the voltage drop across the inductor, VL, and the voltage drop across the capacitor, which is going to be VC. Alright, and so you can see here, I've actually have these drawn at the moment, but I just want to calculate them and see what they are. So if I scroll down here and look at the whole thing, right, remember the E was 100 volts. So these are the vectors. These are the phasors. These are the magnitudes. What I've got drawn here is the magnitude. I've got the magnitude of the voltages. Okay, so that's what we're looking at, but I don't have a phase angle here. So I just I drew the magnitudes of these. And they're to scale, but let's figure out exactly what that is. So if we look at the voltage across the capacitor, for instance, okay, so the voltage across the capacitor is, again, it's going to be Ohm's law. So VC is going to be the current I times the reactance, okay, which has the minus J piece here, minus J times X of C. And so the magnitude of that is, we already have our current. So that's what I like about this Octave software. I already have my current. It's actually, when I display it, is in rectangular form. But I can calculate then VR is going to be I times minus J times 1,000 ohms. Okay, so that gives me my values there, and then I'm going to convert that into polar form. So VR polar, and just this was VR, and this was VR. And so that is 13. All right, so I noticed when I was doing this, my polar form of the current, I actually calculated that incorrectly. I used lowercase I, which of course is the square root of -1. And so my current is actually not 1 milliampere there. It is actually 13.9 milliamperes. That's kind of another nice thing about using the Octave software, because my value of I was correct in there in the rectangular form. It just didn't quite display right, or when I made it polar form because of my typo. But we can see there that the magnitude of the current is 13.9 milliamperes. Okay, so it's 13.9 milliamperes. All right, and so then when I multiply that times 1,000, I get that my voltage here is 13.9 volts, right? This is the voltage, 13.9 volts. So you can see that, right? So it's like about 14 there, almost. And the angle of that, though, look at the angle. Let's flip back and look at the angle. The angle is minus 123 degrees. Okay? So it's at an angle of minus 123.6. So I'm going to make it 124 degrees. Minus 124 degrees. So that's the magnitude of my voltage for the capacitor. Likewise, we can calculate the voltage for the inductive, the voltage drop across the inductor, VL, which is going to be I times a plus J, I times a plus J times X of L. And so again, I've already got in my Octave software here, I already have I in there. So I can say VL is equal to I times, and then J times and 5,000. And so that gives me to it in the rectangular form. Actually, I put in 5,000. I don't really need to do that. I just need to put it in 5, right? Because my current doesn't have the milliamperes in there, and that's why the value showed up. So we have VL, and then if I want to do the polar form, okay, I'm going to change all the R's to L's here, and I will get the polar form of this. And so notice that this angle is plus 56 degrees, okay, 56.3 degrees. All right, so if we look at the voltage VC in polar form, apparently I must have wiped my VC somewhere. But if we look at VC, let's see. guess I used the letters VR for VC. That was incorrect. Okay, that should have been VC there. Okay, so if we look at VC, I just want to kind of point out to you, right, if you look at 56.3 and minus 123. So if we look at the difference in those angles, so we have minus 123.7, and we subtract the 56.3. I just want to point out that this is a 180 degree phase shift. And you could do it the other way. You could say, well, wait a minute, it's 56.3 minus a minus 123.7, right? The fact is it's a 180 degree phase shift. So the capacitive voltage has a phase shift of minus 123 degrees. The inductor voltage has an angle of 56 degrees. The difference between those is 180 degrees. And so let me just write down that voltage value here. So for the VL, it was 69.3 volts. So this was 69.3 volts. And the angle was 56.3 degrees. Okay. And then if we calculate VR, and so if we take VR, that's simply I times R. There's no angle phase shift for R, so it's just times 6,000, or in this case, I'm just going to use the 6. And so that gives me VR, and now I can calculate the polar form of VR, is 83 with an angle of minus 33.7. So it's 83.2 volts. So R down here is, oh, not R, R is the blue one. So R is 83.2 with an angle of minus 33.7 degrees. So those are angles associated with the phasors. So I've drawn the phasors to length. Okay, so I've drawn these phasors to length, and what I want to do is I'm going to try to draw the phasor diagram using this software here and rotating it by the correct degrees. So we already have the scale, so remember the red one down here at the bottom is E. Right, so this is E, which is 100 volts, angle 0. So that one's actually at the correct angle also. So I've got the phasors drawn now, right? So this is the phasor. This is for my source or supply voltage, 100 volts at an angle of 0. And again, these have actually been drawn to scale. I used the Octave software to actually draw these lines to scale. So we have 100 volts with an angle of 0 degrees. And so what we're going to do is we're going to do KVL. And so remember, KVL says that the sum of the voltages, that's a V there, KVL, sum of the voltages must equal 0. So that means that E must equal VR plus VL plus VC. Okay, so the sum of the voltage drops across the loop. And so if I start right here at the starting point of E and I start drawing these, what I have to do though is I have to draw them with the correct angle. So what I'm going to do here is I'm going to select this, and it doesn't matter which one you start with, but in general I kind of like to start with the resistance. Okay, and so I'm going to select that, and so I'm going to select this phasor here, and I'm going to paste it in here. And now remember that it should have an angle of minus 33.7 degrees. So if I come over here to the selection option, and I'm going to rotate this, and I'm going to rotate it clockwise direction, and I don't think this will actually let me do a fraction of a degree. So I'm trying to hit the decimal point and it won't take it. So I'm just going to round up to 34 degrees. Okay, so I'm going to round that up to 34 degrees, and now I'm going to draw this, and I was kind of afraid of that. That's actually not, I'm actually not going to be able to do that at the moment, because the other one's in the way. So I'm gonna grab the green one here, and I'm gonna pull it out of the way. Okay, the 20 was just a scaling thing. It doesn't matter there. These numbers were just from the plot. Okay, so but now I'm gonna grab this again now that I got the green one out of the way. I just didn't want to, and so I'm gonna grab this and paste it back in here. But I'm going to rotate it. So I'm going to go to rotate clockwise, and it's going to be 34 degrees. That's about as close as I'm going to be able to get it using this software. And I'm just going to take this end and put it right there where the red begins. Okay? And so this is my voltage. And so this is my minus 33 degrees right here. Right? So this is minus the 33.7 degrees. It should have been 33.7. It's actually 34. So it's just a hair off. And so now I want to add the green to the end. Down here, I'm going to add the green to the end of the VR. Right, so this is VL, the green is VL, and so I'm going to grab that, and I'm going to rotate it, and this one should be 56.3 degrees. So this is positive direction here, or counterclockwise, and it's going to be 56 degrees, and so I'm going to post that right on here. Now notice what happens here is this voltage actually is touching right here. It's touching the tip of E, but it's going beyond it. Okay, so it's going beyond it. So we're adding VR. So I've taken VR and VL, and I've added those two together, and I'm out here at this tip. And so now I'm going to take VC, the voltage across the capacitor, right? And remember, it's at minus 124 degrees. And so I'm going to rotate it. And again, that was clockwise direction. And 124 degrees. And now notice it's going exactly the opposite direction, and I'm going to paste that right there at the tip of the VL. And notice then that they come back together. They come back together and meet right there, and that graphically satisfies Kirchhoff's voltage law. The sum of the voltages are equal to 0. Okay? So this is what we call a phasor diagram. Okay, so we're using the phasor voltages, and we are adding the voltages, including the angles. Okay, so when you're working with AC circuits, you must include the angles. Okay, and so adding those angles, we can verify Kirchhoff's voltage law. Again, this is referred to as a phasor diagram. And so you can, if your phasors are to scale, you draw this exactly to scale. So you draw the magnitude and draw your angles to scale. You can satisfy Kirchhoff's voltage law for an AC circuit using a phasor diagram.